Hello everyone, this is the senior project final presentation for Capstone 2 Spring 2025. And this is Advanced Computer Graphics. I'm the team leader, Saul Abreu.
I'm Carlos Cruz, the acting as the product owner.
I'm Laura Lou.
I'm Marco Pena.
And I'm Mario Cerra, and we've been working under the guidance of Professor Masoud Sadjadi at FIU, and today we'll be demonstrating our ocean simulation system using advanced graphics techniques.
So let's start with defining the problem that we are addressing. One of the major challenges in creating an ocean simulation is finding the right balance between visual realism and performance. Traditional methods such as Gerstner waves are often limited when it comes to capturing the full complexity of ocean states. They tend to be computationally expensive, which can make it difficult to maintain a stable frame rate during real-time rendering. To overcome these challenges, our project uses Fourier transform techniques. This allows us to decompose and reconstruct intricate wave patterns efficiently, providing a simulation that looks realistic and runs smoothly. We also addressed integrating a dynamic day and night cycle along with realistic atmospheric weather effects, such as volumetric clouds, rain, and thunder. Achieving smooth transitions in lighting and weather creates a more realistic scene for the ocean simulation. Here you can see our project management timeline for the entire semester broken down into 2-week sprints. Our first sprint focused on planning and setup, during which we established our repository, configured the development environment, and finalized our initial requirements. In the second sprint, system design and architecture, we created the high-level design for our major components and used UML and sequence diagrams to clarify how each module would interact with each other. The bulk of our work happened over the next few sprints in module development, where we integrated key features: the camera and input system, the ocean simulation, the day and night cycle, atmospheric weather effects, and our UI layer. We refined each part as we went through these sprints 3 to 5. Finally, during integration and testing in Sprint 6, we merged all modules in the main build and ran thorough tests to ensure performance and reliability.
All right, here are user stories. We built our project around these key user stories here. So user story one was, as a developer, we wanted to create dynamic weather events such as rain and clouds so that the environment feels more engaged and alive in the simulation that we create. User story two, as a developer, wanted to optimize and revise the day and night cycles in the simulation in order to cast a more realistic dynamic lighting. And as user story three, as a developer, we wanted to set up an interface so people could interact with the real-time simulation by changing the pixels, the settings, the coloring, like the amount of how fast the waves are going. So you could do any interaction with the simulation and see yourself the differences. User story four, as a developer, we wanted to implement the Fourier transform waves in order to create more complex dynamic ocean behavior. As user story five, we decided to combine user stories one through four and use the prototype ocean movement with Fourier transform waves and physical based rendering and have the ocean prototype created. By using user story five, we implemented a realistic ocean simulation using the fast Fourier transform to mathematically accurately create the wave generation and movement patterns. The implementation incorporated with physical-based rendering techniques achieved the real realistic water appearance and a proper light interaction, modeling the reflections and refractions and the subsurfaces correctly, making the simulation very accurately and realistic for users to use.
Here on this slide, we have the use case diagram for the main project. Going over at the top row with the user interactions, we have the camera navigation, in which users can freely explore the ocean from different angles and distances. Weather control, where users can select or cycle through weather states, clear, cloudy, rainy, etc. We have weather adjustment, where you can fine-tune rain intensity, cloud coverage, and wind. Time control, manually set time of day or toggle automatic day-night cycle. We have the system functions, going over first the ocean surface simulation, which uses FFT for realistic wave dynamics and reacts to wind and lighting conditions. We have the weather systems, which generates clouds and rain particles, simulates wind affecting the clouds and the rain, as well as the waves, and manages smooth weather transitions. Then we have time and lighting, calculates sun position and updates light direction intensity, adapts sky and ambient lighting to time changes. supports both manual and automatic time progression. Moving forward to the rendering pipeline, we have the scene rendering, which displays ocean with tessellation and displacement, renders the skybox, clouds, and rain with proper lighting, applies time-based lighting to all elements. Then the post-processing, which adds effects like bloom and color grading. It adjusts exposure and atmosphere based on time and weather. And then the output generation, which combines all visuals into the final frame for display. Some key relationships are including weather and time affect lighting, ocean, and sky visuals. User controls influence both systems directly. Time and weather run independently but visually synchronize. And the rendering integrates everything into one cohesive experience. So an overview of the system flow is the user inputs control time and weather. The systems update environmental parameters. Then the rendering engine visualizes the changes. And the final output is displayed to the user. Next, on this slide, we have the sequence diagram for the ocean rendering. So going over first the initialization phase, the ocean parameter setup, it sets the domain size, resolution, and physical parameters. It prepares the GPU resources for simulation. We have the spectrum calculation, which generates wave spectrum based on wind and waves. Ensures physical accuracy with conjugate spectrum. We have the ocean mesh creation, which builds base grid mesh for the ocean surface. It enables the dynamic level of detail via tessellation. And then moving on, we have the per frame simulation cycle. The spectrum evolution for that updates wave spectrum over time, simulates realistic wave motion. The inverse FFT processing converts the frequency data to spatial wave displacement. It uses horizontal and vertical FFT passes with ping pong buffers. And the texture assembly produces displacement and slope maps, which prepares data for lighting and rendering. Then we're going on to the rendering phase. We have the texture binding first, which binds all the simulation textures like the displacement, slope, the foam. It ensures proper MIP mapping and effect layers. The frame buffer setup prepares render targets with color depth formats. Sets up buffers for post-processing. The shader configuration sets camera view, transforms, and lighting. Binds necessary textures and inputs. The ocean surface rendering activates tessellation for dynamic surface detail. It applies shading for reflection, refraction, and highlights. And the post-processing adds final effects like screen space reflection and depth cues. It outputs the final rendered image. Some key technical highlights: the FFT-based simulation is efficient, realistic wave generation using frequency domain. The GPU acceleration compute shaders and tessellation for real-time performance. And the texture-based design simulation stored in textures for high detail visuals and effects. And the result is a fully simulated and rendered ocean that reacts dynamically to environmental inputs while maintaining real-time performance.
All right, here are the systems assigned, the architecture of our simulation, what is needed to run this. So for the hardware, we had NVIDIA or AMD GPU because it's necessary to run this simulation. You could use, if you don't have a proper GPU, it might not fully work, you know. If you have an NVIDIA GPU or AMD GPU, it is necessary because without them, it will not work. If you have a better CPU, it is recommended to use an Intel CPU because it will work better flawlessly with both of them being the best part in your system to run it, because it might have some bugs and glitches if you don't have the proper NVIDIA or AMD GPU. And if you have a better one, it would even improve the frame rate that you could get for it. So it is very recommended to use both of them, the best quality, the best product to run it. For the parts that as a team members we all contributed, we use mostly OpenGL. With OpenGL, we learn, all of us, because we were not very familiar with the content, but we knew about them, but we were not very familiar. We read through all their procedures and how it works, how it should be implemented with Visual Studios. And like I said, we all had NVIDIA and Intel and ran the simulation through there. It worked good. It looked very realistic. So that's why we implemented and contributed to all of this. We all combined our code with GitHub. We got our images from DearMU. So we all use the same softwares and libraries to run our code. So it is, you know, we are, you know, intertwined. When, you know, if we didn't know, we'll, tell them the library. So, and at the end of the day, you know, we all contributed equally in our projects and showed what could be capable of with a simulation as hard as it could be. Okay, so system design again, but this was the deployment one. So for the deployment, we decided to go with an OpenGL pipeline because we mostly use OpenGL. Without OpenGL, we will not be able to decide the shader, what type of geometry we wanted the simulation to be, how it should be, what should be the background, how should the waves interact with the ground. So we use OpenGL to make those changes in the simulation, So because it is very important to see the difference between the pixels when you add the user interface to the simulation to see the ocean movement in different variables with different colors. So we had to use a similar pipeline example here of how the deployment of the program, what's going to run and how it should be implemented for the users to use and see the differences.
Okay, so moving on, we have a basic UML class diagram to show how the main components of our simulation function together. The ocean class handles realistic water simulation using the Fourier transforms so that we can have that dynamic wave behavior. Then we have this weather system class, which manages the atmospheric effects. As you can see, we have the volumetric clouds, the rain, and the thunder. Then we have the day-night cycle, which controls the lighting transitions between day and night. And then we have, from all of these, the main renderer class, which coordinates these components to ensure each frame is updated and rendered in the proper sequence. Finally, the window class sets up our OpenGL context and manages user input. Together, all these classes form our integrated system.
This is the core of our ocean simulation, and it relies on three key functions. First, we have the evolve spectrum function. This handles the time evolution of ocean waves. It iterates through each wave frequency component, both in the x and z directions, and applies the evolution formula, which can be seen as h of k comma t. This gives us the updated wave heights in the frequency domain, which we store in a texture. Next, we have the inverse fast Fourier transform function. This step transforms our data from frequency space back into real-world spatial coordinates. We apply this function first along the horizontal axis, then the vertical axis, and then the result is the actual height and displacement textures that visually drive the ocean surface. Finally, we have the assemble textures function. Here, we normalize the data, generate displacement and normal maps, and pack everything into textures that are used during rendering for lighting and shading. Here we have our test suites and test cases. The first test case is the spectral parameter testing, where we tested different texture sizes, spectrum depths, and waves generating parameters, assessing how they affect both quality and performance across various solutions. Visual fidelity testing is the next one, and this test includes checking the realism of ocean color, transparency, and wave patterns, as well as how foam and bubble affects behaviors. Render parameter tuning is the next one, which we adjust settings like surface roughness and light scatter and analyze how the ocean interacts with the environment lighting, all while optimizing for performance. The final test, we made sure the user interface is responsive and easy to use, allowing real-time changes with immediate visual results. Here's a summary of our project. We successfully developed and integrated a physical-based ocean simulation using Fourier transforms. The result is mathematically accurate wave behavior with visually realistic water dynamics. The system is optimized to run in real time and can even run on a laptop despite its heavy GPU usage. This includes memory and performance tuning to support interactive rendering. And here we have our reference list.
And finally, before we conclude, on behalf of our entire team, we'd like to extend our sincere thanks to Professor Masoud Sadjadi. Your guidance and challenges throughout these Capstone 1 and 2 courses have been invaluable. We'd also like to thank the FIU School of Computing and Information Sciences for providing the facilities and support that enabled us to complete this project. Thank you.